tunnel. So you have a very deep lattice, but then you start to decrease the lattice and then let the atoms tunnel. Well, if its unit is fully occupied, then Pauli statistics is going to prevent the particles to tunnel. You are going to have here, you are going to have this particle here, no tunneling, but because this atom cannot go here because it's already occupied. So in principle, his idea is let's try to do the system as dense as possible, one atom per side, and if we go very shallow, then we are going to prevent motion, double occupancy, perfect. So that's the dream. And in principle, 2 years ago, the experiment was able to report very high filling fraction. So we are talking about a spin polarized gas, and they were reporting about 0.9 filling fraction at the center of the lattice. That is very good. It's very good, but it's not enough, yes, first. And second, because of a spin orbit coupling, unfortunately, even though we start to have prepare everything in the ground state, when you start to drive the atoms, again, so this goes, for example, along the x direction, and the other atom goes along the minus x direction, then just because of the poles, you are creating a distinguishable state. And now this condition of Pauli exclusion principle is not anymore satisfied, and the atoms start to tunnel. So the atoms start to tunnel, and then, well, you have to start to deal with double occupancy. So there is no way that we are not going to need to understand atoms tunneling in a lattice in order to include the clock. So that's going to be all our story today. We are going to study atoms moving in lattices, and we are going to see how these things either affect the clock or how we are going to use the clock to probe all the physics that we want. So that's, again, this barrage. Now, let's try to think about what is the simplest Hamiltonian that describes alkaline air atoms in a lattice. And we are going to first start general. So we are not going to consider that we have spin polarized atoms, but we are going to assume that we have atoms that are in all different nuclear spins configurations. The idea, and one of the biggest advantage of having SUN degrees of freedom, is that cooling can be faster and better. So if you have atoms that have fermionic particles, when you are going to cool them down, for example, if they are spin polarized, there is no way to cool them down because the cooling requires collisions, yes? When you cool particles, the way that you cool them is via evaporative cooling in the last stages, and for evaporative cooling, it relies on the process of rethermalization. The hotter particles collide. It's like imagine that you have a cup of coffee, but it's in a trap. You are going to have particles populating these different harmonic oscillator levels. You are going to let the particles escape, and basically the hottest particles leak, and only the coldest particles remain. That's the idea of evaporative cooling. But for that, you need to rethermalize the particles that remain here. Otherwise, well, there is no decrease in phase space. In order to rethermalize, what you need to have is collisions that are good elastic collisions. And if you have, for example, spin polarized gases, they cannot collide because of Fermi exclusion principle, as we discussed last time. Nuclear spin polarized atoms, they don't collide via S wave, and P wave is too small to thermalize the gas. But now, imagine that instead of having a spin polarized, you have a spin 1/2. Well, there are possibilities. Half of the time, the atoms, or well, no, one quarter of the time, the atoms can collide, because if you have two particles, you can have down, down, up, up, down, down. You can have the triplets, and you can have the singlets. And therefore, these cannot collide, but these can collide. So at least we start to gain something. When you are starting to have more flavors, then instead of having the possibility of having a single type of antisymmetric state, you are going to enhance the statistics. If you have SUN particles, you are going to have n minus 1 divided by 2 possibilities of collisions. Yes, because if you are 9½ can collide with the 7½, a 9½ can collide with the 5½. So you are going to increase the rates of collisions, and we are going to reach colder temperatures. So that was one of the reasons why we wanted to use SUN for preparation. And then, well, there is the trick that you need to start preparing the atoms and the number of nuclear spin states that you want. But okay, so, but the possibility to have faster cooling has been explored not only in strontium atoms, but there are experiments in ytterbium by Takahashi, for example, in Japan, that they have seen the fast rethermalization that is allowed by SUN. So in this case, we are going to always satisfy the condition that if you have an optical lattice, when you have looking at the lowest, at the different bands of the lattice, the condition of being in the lowest band is very well satisfied. So all the particles are going to be in the lowest band of an optical lattice, and we're going to characterize the eigenstates of a single lattice site in a very deep lattice in terms of Warnier states, yes? And then, because we satisfy this condition, the Hamiltonian is going to be very simple. You are going to have the possibility to tunnel between the different lattice sites, because we have a magic lattice. What happens is that the tunneling rate, even though could be depending on the different type of particles, of course it's not depending on the nuclear spin, could be depending on the excited state, but if you have a magic lattice, then what happens? It's the same. It's the same. There is no difference. So there is the tunneling. We are going to assume the part tunnelings only near neighbors from simplicity, and then we're going to include the interactions. So remember yesterday we write the complicated Hamiltonian that had inter-spin interactions, direct and exchange. We were writing in terms of field operators. Here it's much simpler because we are going to have write the field operators in terms of Warnier star states and only account for local interactions, because the non-local interactions are going to be suppressed by, they're very small. So in that case, the type of interactions that we can have is going to be calculated as usual in the Hobart model. You have the Warnier star states at a given lattice site, and the interaction strain is going to be set by the overlap between the wave functions, and in this case multiplied by the scattering length. That is different, depends on the different states. Yes? Hmm? Hmm?
If you don't, like, if you don't use a magic lattice, then the ground state and the excited state are going to feel a different lattice. Like,
Yes.
there is a shift.
Yes.
And it's actually the opposite, or like?
Is in general, we are going to have, I'm going to go through that direction at the end. Hopefully I managed to go that. But I mean, I think what in that case, you are going to have grounding Warnier star state at lattice site 0, for example, but you are going to add an index sigma. That depends of a spin up because it's different. So the tunneling is different, and then you're going to have, of course, you're going to have everything going to be replaced. So, for example, if you're going to have exchange interactions, the exchange interactions that we are going to be, the next is going to be proportional to Warnier star state square. So you are going to have of the up square, of the down square, dx are interactions that involve the two states, the two states. This is up G and E. So you will have just to correct for the fact that they have different Warnier states.
Okay.
And therefore the tunneling, that is the overlap between Warnier states
Yeah,
and
it
different
changes.
lattice sites. So
Yeah.
the tunneling rate always is computed by the overlap between the Warnier lattice site at site I, the single particle Hamiltonian that include the kinetic energy and the lattice potential, and the Warnier lattice site along the next. So X, so yes. So now you're going to have an alpha here for the tunneling. This is proportionality. All right. So now, if we look at the interactions, therefore, we are going to translate the different interactions that we also discussed yesterday. So we are going to have intra-orbital direct interactions. So we are going to have particles all in the ground clock state is going to be UGG. If you are going to have atoms in the excited state, it's going to be UEE. This is, and you might be familiar with this type of interactions. In the Hobart model, you are going to have, typically you have these interactions, for example, as n up at side, maybe n up at side I and down at side I. Yes? This is exactly the same as writing, because the total number of particles is conserved. It's exactly like that. Sorry, -1, like that, when n is associated with the total number of particles. Yes, but here you are going to have here alpha is going to be an E for the case of UEE, and then for the case of UGG, you are going to have, so I have to have here two index different. And then it's going to be NG -1 times UEE here times UGG. Yes, this is a standard type of interactions in the Hobart model. Independent of the only scattering length depends on if you have in the ground or in the excited, not on the nuclear spin. That's the SUN character of the interaction. Yes. Now the next term is what we call direct interactions, that is going to be proportional to the number of particles at lattice site I in spin J and the number of particles at lattice site I in state E. So always, again, all the time that I'm writing, if I don't write a subscript M, that is the nuclear spin, N of EG is going to be sum of N EGM. Yes, I'm summing over the nuclear spins. Is the population of all the total number of atoms in ground independent of the nuclear spin. I always sum for that. So there is here. And the last term is the exchange interaction. And the exchange interaction is the one that is not diagonal. And this exchange interaction means that I have a particle in state E and nuclear spin state M, state G, nuclear spin state P. And then after the collision, what happens is that they exchange the nuclear spin. So if P was the subscript associated with the ground state, now is M, and is M was the nuclear spin associated with the excited state, now is P. The exchange. That is called exchange interactions. And then the coefficient is the difference between UEG plus and UEG minus. So this is the most general Hamiltonian, and this is the Hamiltonian that we are going to deal here. And variance of it depends on what we have. So sometimes we are going to have not this term because the system is going to be spin polarized, or sometimes we are going to have all. So I want to start by one of the very cute experiments that was done exploring the SUN symmetry for the first time. This is experiments that were done by Max Planck at Munich and also in Italy, at Florence. So this tried to understand the SUN character of the interactions by probing the mechanism of exchange interactions. So the experiment operated in this way. For ytterbium-173, N is equal to 6. So for ytterbium-173, you have the nuclear spin is 6 because you have phi half all to minus half phi. So all these different combination of nuclear spin. I is equal to, I is equal to phi half. Now, so in the experiment, they have a 3D lattice. At the moment, we're going to forget about tunneling. And what they did is that they were able to populate sites with only in the ground state. So yes, they start by populating sites with atoms in the ground state. And with that, if you have two atoms in the ground state in the same lattice site, they have to have different nuclear spins, because otherwise you cannot satisfy Pauli statistics. So in the notation that I'm going to use is going to be exactly what we have in this picture. Maybe it's easier to see here. I'm going to write, everything is in the lowest band, but I'm going to write the ground state with red, for example, and the excited state with blue. And I'm going to have two different nuclear states. Let me assume that we start with 5½ and 3½. So the idea of the experiment was the following. Let's start with these atoms in the ground state. And then we're going to start driving these atoms. We drive these atoms with a laser that we can do. And we are going to drive these atoms into an state. So what they wanted to do initially is to drive this state into this state. One atom here and one atom here. That was the idea. And then, because this is not an eigenstate of the system, then the idea is that after this is done, then we are going to start the process where this goes up, this goes down, and then we're going to have these exchange interactions, and these exchange interactions are at a rate that is proportional to B exchange. That's the whole of the experiment. So, but let's look a little bit of details and complications. So the question is, if you have two atoms in the ground state, how you're going to drive a state that is the particle in the ground, the particle that is in the ground state is in a spin. Okay, let me put this maybe down. Let's call this a spin up. How we're going to do the case where the particle in the ground state have a spin down and the particle in excited state have a spin up. How we're going to do that? The only possibility to do that is to have a magnetic field that is going to split the energy between this state and this state. So basically, and this is what is wrong here, if I have, remember that I told you that atoms in the excited state have different G factor. So in the presence of a magnetic field, the particles in the ground state have, let's imagine, very weak Schumann level, and in the excited state, these are going to have a more significant splitting, and this splitting between these levels is delta B. Yes? So if I ignore the magnetic field, and these two are degenerated as I was writing in the blackboard, set delta B equal to 0, then as we discussed yesterday, the eigenstate of the system, given that the particles are in the ground state, has to be totally antisymmetric. And the only way that you can construct a totally antisymmetric state is the particles are symmetric in the orbital and antisymmetric in the spin, or antisymmetric in the orbital and symmetric in the spin. Yes, that's the only states. And we discussed yesterday, this state has energy proportional, interaction energy proportional to the scattering length Ag plus, and this has interaction proportional to the scattering length Ag minus. Now, in the presence of a magnetic field, because it's different for the ground and the excited state, the magnetic field doesn't want to favor triplet or singlet, but a superposition of triplet and singlets that are the state, this state, I mean, let's put this here, put it here. So it's either this state is one of the states, or this state, this state here, or this state, when the particle, I mean, one state here, or one state here. These are the two possible states. And therefore, the Hamiltonian in this basis is going to see that you have the interactions between these two states, plus and minus, and the magnetic field wants to couple them. Yes? So in the experiment, and this is the first exercise that I want you to do, maybe you can start doing with your neighbor, or you can do it by yourself, but I just want you to show that if you start with the particles in this state, I mean, this is going to the initial state, the one that I'm showing perhaps here. If you start in this state, the particle in the excited state is in down, and the particle in the ground state is in up. In this initial state, there is a superposition between these two states. I prepare this state. This state is an eigenstate of the Hamiltonian if delta B is huge. So you know if delta B is huge, this is the eigenstate of this Hamiltonian. And then you turn off the delta B, the magnetic field. And then the experiment, what it did is measure the population or the probability of being, of having an atom, of having an atom, atoms in the ground state up. Then I want you to work out in your paper that this satisfies this expression. I give you 5 minutes. Okay, so I'm going to give you, because so this, the key part is that this Hamiltonian can be written. Remember that this Hamiltonian has B exchange is the sum of this, is the difference between the two, and B is the sum of these two. So this Hamiltonian can be written as B, the identity matrix times B. But the important part is that you are going to have a Hamiltonian that has B exchange, or 2B exchange minus 2B exchange. You have delta B, yes? So basically this Hamiltonian can be written as a well, 1/2. And this is 2, 2. So this Hamiltonian can be written as 2B exchange SC plus 2 delta B sigma SX in this 2 by 2 level, yes? We turn off this part, and then what happens is that you are going to have a Hamiltonian with SC, and in this Hamiltonian SC, then in this basis, the states that are up, the up and the down states are the plus and the minus. Sometimes, to make the calculation sometimes easier, it's just you change the basis, you do a pi half rotation along the x direction, and then this Hamiltonian can be written as 2B exchange SX, where now the coordinates, this is the states that we have. There are two states, E down, G up. This is one of the states, and the other state is G up, G down, yes? And basically, in this state, I'm going to start in a state that here, it's superposition. I'm going to start in this state. Yes, I'm going to start in this state, and the Hamiltonian is Sx. So what is happening? I'm going to start precessing around the x direction. So if I have a magnetic field along the x direction of this block sphere, I start up. I'm going to do rapid rotations, rapid oscillations, and therefore I'm going to, what I'm talking about is what is the probability of I'm going to be in up state. So clearly, you're going to see is the rapid, what is the precession rate? Is going to be the magnetic field, that is 2bx, and I'm at time equal to 0, you start with all atoms in the up state, effective up state, and you're going to evolve periodically with this rate. Yes? All clear? So, and exactly this is what the experiment saw very nicely. They were trying to see some rapid oscillations. But as a function of time, they see the oscillations started to decay. The interesting part is that these oscillations were going to tell them the value of B exchange that they didn't know. As I said, computing these parameters is hard. So they started to look at the B exchange interactions, and they repeat this experiment with not only 5 and 3 halves, but they repeated with all different combination of nuclear spins, and they saw the same rate. So this confirmed the SUN character of the Hamiltonian. But unfortunately, when they were trying to look at the oscillations, and even when they were trying to prepare the initial state is an eigenstate. So this initial state is an eigenstate of this delta B Hamiltonian. They were having problems. It was super hard for them to prepare the atoms in this state. And after they did the experiment, they understood why. Look, when they look at the scattering lengths and they were trying to fit what is the value of B exchange, they found that one of the scattering lengths was normal, 200 atomic units, but the other scattering length was huge, 3,000 atomic units. This is crazy. This is very strong. And that's why they were having problems with creating the initial state, because they had to increase the magnetic field a lot in order to polarize the states. So later, and they were seeing losses. You can see the oscillations were decaying. So later, theorists understood what was going on, And I don't know who has heard about Feshbach resonance. Okay, Feshbach resonance is is a type of resonance that happens when particles collide, when you have a closed channel and an open channel. This is the closed channel. That is a molecular channel, and an open channel, that is the collision of the two particles, and where the open channel become unresonant with the molecule channel, then they favor the particles to bound, and they can significantly change the scattering length. This has been seen in alkali atoms. In alkaline earth atoms, this cannot happen because we are talking about nuclear spins. The magnetic sensitivity is super small, but theorists found out that there is a similar of a Feshbach resonance. I mean, in this case, this is as a function of R, the separation between the particles. But they found that similar type of Feshbach resonance can occur between orbital states in alkaline atoms. They call orbital Feshbach resonance. And there has been a lot of continuation of this and exploration of that. But the bad news, fortunately for ytterbium, is that it started to tell the experimentalists that ytterbium-173 might not be the best to explore SUN magnetism, because you are going to have a lot of losses in the problem. So that was one of the revelations that we had. Okay, now I want to go from two atoms to many atoms. So we are going to stick ourselves to single lattice sites. Single lattice sites. So now instead of, for example, I'm going to have more nuclear spin levels, for example, and I'm going to, and we are going to start by assuming that we are always populating an state that has the atoms in the ground state, but of course in different nuclear spin states. So if we start with two atoms only, then if, for example, I start, I can even put it more states. These are nuclear spin states, for example. If I start with two atoms here, one of the questions, can I populate states here, here, or here by collisions? No, because this is the SUN symmetry. The SUN symmetry conserves the nuclear spins. So if I have only two atoms, the only type of superspace that I can remain is conserve the nuclear spin. I can call this, I'm going to apologize because I changed here the notation because it's going to be easier to have up and down for E and G, and I'm going to write a color of the nuclear spins with a color. So if I have now, this let me call this down and this up. This are going to be G and E. And then let's try to see what are the states. Well, for the case of for the case of two particles, we already noticed them down, the one. So they are going to have, we are restricted to only one atom in the excited state. Only one atom in the excited state. So the possibility is having both in the ground state, and then you are going to have an antisymmetric state in the color. That is going to be a singlet in the color. Then we're going to have the triplet, and again, antisymmetric state in the color. And if you're going to have a singlet in the orbital, and I'm going to have a triplet state in the color. For dealing with fermions, I don't know if you have ever dealt with fermions and you have to do exact diagonalizations, but one of the ways that I like to keep track of the possible states that you have is by going to second quantization and labeling all the possible states that you can have. For example, if you have, in this case, we're going to have a single lattice site, and I'm going to have these states as ground and these states as excited. And the way that I'm going to fill up a Fermi state is that I can have only one particle per level. That's always the condition. And for example, this is very useful because if you have, for example, a process that you have, for example, that couples, for example, an state with one atom here in this configuration to a state where these particles jump into this state. So we're going to have this, let me write it equivalent, this, this. So this is equal to this is equal to this. So if you have a process where this particle jumps into this site, that is this state, you can see that by jumping one particle, you get a minus sign. This is the best way to keep track of the minus sign for fermionic particles. If you ever have to do a diagonalization and want to keep track of the minus signs, that's the best way that you can draw. So in this case, for the state that has, for example, for a singlet state, in this case we're talking about only two states, and then we're going to create one particle in two different configurations. This is the only state. So this is going to be an operator that creates a particle in the first state and the other that creates a particle in the second state from the vacuum. So that's the singlet state. That's how we write it. It's the singlet is an SU2 singlet. We all know that. But now let's go to the case when we have three particles. What are the possible states? If you have three particles, and then you're going to have three different flavors. So the simplest state is, and remember, only one particle can be, at most one particle can be in the excited state. So the possible configurations are, you can have all the particles in the ground state, mean all down, and then the state has to be in an antisymmetric state for all these three flavors. This is called SU3 singlet. This is the state that I'm. Now, the other easiest state to understand is a state that you have all the orbital degrees of freedom symmetrized, and you again antisymmetrize in the flavors, in the nuclear spins. The state is a little bit non-trivial, and again, this spin 3 singlet is to create or write in second quantization because you create a fermion in color or in nuclear spin 3, nuclear spin 2, and nuclear spin 1. This is the state. Now, the state that's a little bit non-trivial is the state, okay, and people call these states W states, I don't know, the states with only one spin flip and fully symmetrized. The state that is perhaps not fully trivial is the remaining states. But let me ask you, if I have fermionic atoms, and I tell you I have n atoms, and I have n nuclear spins, and I have, or maybe I am using the notation here, yes, I have little n nuclear spins for simplicity, little n nuclear spins, how many states I can have with one atom in the excited state and with at most one atom in the excited state? How many possible states can I have? I have n atoms, and I have n nuclear spin states. So, for example, let's go for the case of 3 atoms. If you have 3 atoms, and we have 3 flavors, how many possible states with one atom in the excited state? So it's easy to see in this diagram. So what happens is that, look, let's maybe for simplicity make this the same. For simplicity, let's be Ni equal to N. So in this case, what is going to happen is that I'm going to put, if I have one particle in the excited state, then how many different possibilities I have? N, yes? And then what I do is that I can put my remaining atoms. So if I put one atom here, I have to put my other remaining atoms in all other states different from this one. Yes? So that means if I have, so there is only one way. If I put my excited atom here, I have to put my remaining atoms in the other. If I have my atom here, then I have to put the other remaining atoms in the other states that are not this. So these are the n states. So that's why, in this case, you can see if you have 3 particles, then I have 1 state and other 2 states here by a total of 3, as expected. Yes? Now, the energy of this state is 3 UEG. The energy of this state you can compute, and maybe we can do it in the tutorial. When we do that, is UEG plus 2EG plus. It has to be EG plus because it's all the particles in a symmetrized state. And then this has a little bit of different configuration, more complicated. If you have now n atoms, you have n atoms, and one of these is in excited state E, the possible states that you are going to have is all the particles are in the ground state and you have ISU n singlet. You can have all the particles in the symmetric state of the orbitals and a singlet state. And the more complicated states are n minus 1 states, where you have, it's not fully symmetrized in anything, not fully antisymmetrized in anything, but you can have different type of configurations when you can see that the state is in the excited state changes position from being, from being all in the last one, in the prior one, and so forth, and you have to antisymmetrize. So this looks a little bit obscure, but why I'm telling you that? Because we did an experiment where we measure all of this. So, and the important part is that all of these are SUN singlets that are really a non-trivial state. So what were experiments that we did? We put all the atoms in the 3D optical lattice clock, and then we can have a occupation of 1 atom, 2 atom, 3 atom, 4 atom, up to 5 atoms in a given lattice site. Then what they did is that we shine the atoms with a laser that drives population between the ground and excited state. And then we scan the detuning of the laser and look as a function of the detuning of the laser when we get population transfer. So if I have 1 atom, how many peaks do you expect to see? Or how many resonance that you expect to see? I have 1 atom in a given lattice site. How many resonance I expect to have? Only 1. If I have 1 atom in the ground state, I'm going to have, when my laser, this is what we discussed yesterday, when I have a detuning equal to 0, when in the detuning, when the laser detuning, okay, this is the laser minus the atomic transition. When this is equal to 0, I'm going to transfer all my atoms from the ground to the excited state. Yes? So that's what you see here. If you have 1 atom, and then we are going to have a peak, then we are going to have, I set this peak, this detuning as my resonant detuning, and at this part, I'm going to transfer my atom from the ground to excited state. Yes? You all with me? Now, what happens if I have 2 atoms in the same lattice site? How many peaks I am going to see? I have 2 atoms. And these 2 atoms are going to be with interaction UGG because are in the ground state. If I'm going to excite 1 atom from the ground to excited state, the other states are going to be UEG plus and UEG minus. So when I'm going to scan my detuning, when I'm going to see a peak? When the detuning, set from this, this is omega L minus omega L. This is omega L minus omega A. That is, let me put this delta 0, maybe for simplicity. But then when the detuning is equal to the energy difference between these 2 states. So we are going to have EG plus minus UGG. There is one peak, but there is another peak that I want to see when this is UEG minus UGG. And let's see. That's exactly what we see. We see two peaks. Now, when we have three particles, how many peaks are going to see? No, that's the advantage of SUN, 2. This is the slide that I was trying to show here. If you have 3 atoms, again, there is going to be only one with this energy, that is the fully symmetric and the antisymmetric state, and any other configuration, because of the SUN symmetry, has the same energy. So I will see 2. So this is exactly what the experiment saw. With 3, we have only 2 peaks. If I have 4 atoms, how many peaks I'm going to see, resonance peaks I'm going to see? 2, exactly, and this is what the experiment saw. This is the evidence of SUN symmetry. We only saw 2 peaks, very nicely. There is a decay in the resonance amplitude, because when you have more than 2 atom terciles, when you start to have 3, 4, you are going to have what is called 3-body decay, 3-body recommendations, and this introduces some decay, but we are able to see up to 5 particles per side. So with this procedure, we were able to calibrate again the scattering lengths, EG and EG minus, for the 2 particles. So when you have 2 particles, we remember that we are going to see these 2 peaks, and with these 2 peaks, we were going to see the amplitudes of the different scattering, the scattering lengths, and that's how we calibrate. Exactly, as we expected, we get the amplitudes of these 2 scattering lengths. But then we try to compare our calculations with the experiment. This position of the resonance compared to what we expected from the SUN hover model. And what we saw, to our surprise, is that we agree for 2 particles, but when we were to 3, 4, 5, our predictions of the peaks of the resonance were off. What do you think that could be happening? To a surprise, and this is next discussion that I'm going to have, we were seeing signatures of multi-body interactions. So in gauge theories, in many aspects of condensed matter physics, you need not only 2-body interactions. For the Kitaev model, for many things, you need multi-body interactions, many particles interacting at the same time. Well, that's exactly what we saw. But we were sad because our model was not fitting, that we thought that we have all the perfect description of SU8 magnetism. So for that, I want to go back where the first evidence of multi-body interactions were shown in optical lattice. And this was an experiment done by Sebastian Will back in 2010, where they surprised for the first time we were seeing a time-resolved observation of coherent multi-body interaction in quantum phase revivals. And the physics that we are going to be seeing here is very similar to that, but I'm going to explain a little bit how was this experiment. So this experiment was done by exploring what is called collapses and revivals. Anyone is familiar with this type of physics, collapses, when people talk about collapses and revivals? Collapses and revivals are oscillations that you see in a many-body system that are periodic, but not necessarily caused by single particle physics. It's not time crystals or nothing like that, but it's just oscillations that emerge because you have a very pristine periodic or simple parameter Hamiltonian. So let's go back to the hover model, for example, or we are going to restrict again to atoms, to have atoms only in one orbital state, and the Hamiltonian becomes U is equal to n minus 1 divided by 2. This is the interactions. So that means that the spectrum is going to be, well, if you have 1 particle, if you have 0 particles, you have 0 energy. If you have 1 particle, you have 0 energy. You have 2 particles, you have U. If you have 3 particles, you have 3U, and so forth. Yes? So the spectrum is integer value of U. So what the experiment did is that if you start with a superfluid system, in this case, so we have an initial state. Imagine that you have an initial state where the initial state is a superposition in a given lattice site of having different occupations of L. A superposition. You can have a state with 0, 1, 2, 3, a coherent state. So you have a shallow lattice, you prepare your system with a Poissonian occupation of different lattice sites, and you turn on the lattice and make it very deep. Then the experiment, what they did is by time of flight, they were able to measure the expectation value of the operator A that destroy a particle in that lattice site. So what happened? When they look at the measurements, they were looking at what they expect to see is these beautiful collapses and revivals. And the reason is that if you look at what is the expectation value of A, so when you apply the operator A to an initial, if you have this system, you let it evolve only with the interactions, the dynamics is very simple because you are going to have something like E to the N times T. Yes, that's the only dynamics that depends on the number of atoms per side. You're going to have a different phase. You are in a state of the system. Now, if you measure the expectation value of A, the expectation value of A changes N to N minus 1. Yes? And therefore, you are going to see that when you compute the expectation value of A, the only thing that matters is the difference in energy between E sub N and E sub N minus 1. And this difference is just U. And therefore, all the different states have the same frequency. And that's what you're going to see. This, again, we have a lot of cosine on this talk, end of this part, cosine of U. And they expect to see these very beautiful periodic oscillations. But that's what they saw in the experiment. They were not so periodic. So what was the explanation? The explanation was related to the emergence of multi-body interactions. It's not that we have multi-body interactions in nature, but the body interactions emerge as a virtual process. The point is that if I start to have more atoms in a single lattice site, so now this is the lowest band, and I'm going to start to put atoms here. We were using the lowest band Hamiltonian. Yes, that's what we were restricting. But as I start to have more particles, the interaction energy grows and grows, and therefore, it becomes not negligible, the interaction energy of this many-body state compared with h bar omega. That is the energy splitting of the band. And even though not totally resonance, interactions have the possibility, because the Warnier-Stark states are not eigenstate of the interactions, interactions have the possibility to transfer atoms from this band to this band. There is no problem. There are matrix elements in the Hamiltonian that transfer interactions between the lowest band to the first band. So what is happening? So what if you have a system that is with all the particles in the lowest band, for example, and you have a matrix element that transfer this to an excited state, this nevertheless can be all resonant, cause energy, and then you have to come back. So we are going to have a virtual process, and what happens is that to leading order, you are going to have process where you have a particle in the ground state, you go up, and they go down. Yes? And then you can do even higher order process. You can have particles, two particles go up, and then there is an intermediate process between them, and then you go down. So you can have more complicated processes. And in order to account for them, you have to resum all of them. It's not a very easy task. I mean, there is kind of, the people quote field theories to try to renormalize and to sum of all the diagrams. But effectively, this process gives rise to multi-body interactions, because only happens when you start to have 3, 4, 5, and so forth, all these particles. So, question?
And this happened, can you come back? One.
Yes.
And this happened in really deep lattices.
It happens in deep lattices. It's worse in shallower lattice, but I think what I'm doing here is signaling tunneling. So
In every lattice, though.
in every lattice that is filled with more than 2 atoms, then you can have this process.
Is there a lattice, I don't know, frequency or wavelength or regime of parameters that this can be avoided?
There can be very small, yes. In principle, they're very small because these are going to be, the process that we are talking about is going to have, you can see, it's going to be weighted. I mean, it's going to be, basically the process that we are talking about is, I mean, the effective Hamiltonian that we have is going to be, we have the initial state, you have the interaction Hamiltonian that, for example, for second order, you have the interaction Hamiltonian that transfer one of these particles to the excited band. You are going to have the intermediate state here, this intermediate state. This intermediate state has energy h bar omega more because of this process, and then you're going to have the interaction Hamiltonian that brings you back, yes? So this process is going to be a term that is going to be U squared divided by the interaction, I mean, by the band gap. This is the rate of this process. So the deeper the lattice, this is much quicker, and the deeper the smaller the U, weaker. So it's a compromise on how it scales with lattice depth. But typically you have them. The point is that it's hard to see them. These experiments that saw it in a manual, they have to go to very long times to be able to see them. And in the clock, we were going to see it because the clock is super precise, that is able to resolve even these tiny effects. But they made a difference. So I think you always have to include them when there are more than 3 atoms per size, but maybe it's just a small correction that you cannot. Yes, so when you can write this effective Hamiltonian, and I'm not going to enter the detail, but the result is that this SUN Hamiltonian that you had before, remember you have the ground state, the direct, and the exchange, is going to be modified by processes that have 3 body terms. In the multiplication of, you can see operators that have 3 particles in the ground state. These are 3 body operators that vanish when you have only 2 particles. And you can include the corrections from 4 body and so forth. It's a mess, but you can do it. And when we do it, without fitting parameters, you can see that before the lines that we were calculating were not agreeing with the experiment as we include up to 4 body interactions, we were able to reproduce the experiment. So what I'm showing here is how you can see how precise are these experiments, that it allows to see these multi-body interactions in a way that no one has seen them before.
Thanks. So no, like this graph, in the previous version of this graph that you showed without the corrections, you still had a feature that remains here, which is that the lower energy ones, the ones that are closer to 0 detuning, looked good, and even without the many body corrections, they already looked good, but it was the higher detuning ones that were off. It's still the case here, less so. I just wanted to know if there's like a deeper reason for that.
Yes, because the more particles that you have, the larger the interaction energy compared to h bar omega. So these corrections, I mean, maybe I should have, I mean, this is minus some. So the important part is the difference in interaction. I mean, maybe there is a U here. I mean, this expression with this was in the regime that U was small. But when you have here, you are going to have the energy of the state. So the larger the interactions of the particles, the closer to the band gap, and therefore the most important are these processes for that. So Yes, so I mean, I don't have the, yes, so it's just these effective terms are going to scale like the difference between omega and the energy of the initial state. So they deviate more and more, and that's yes. So, but I mean, this is where we started to see first modification of what we have with only SU2 system in fermions. Okay, so now let's go to allow the system to tunnel. So far, I have particles in a lattice, and we study all the different single-site physics. That is a little bit boring. I mean, it's exciting in the sense that you can see all these corrections, but are tiny corrections. Let's now to go to the more complicated regime when we are start allowing the particles to tunnel. So let's try. How many of you have derived in the past super exchange interactions? No? So let's do. He derived this. Uh-huh. He did it. Okay, so you are all prepared. So I will ask you to repeat, go back to this memory line, and in the next 10 minutes, derive the super exchange model. Okay, the problem is the following. I'm going to have, this is going to be, we're going to go back to spin 1/2, or nuclear spin polarized fermions with internal state EG. A spin up and a spin down fermions. And what we are going to have is the following. I'm going to have the particles in the lowest band. And what I want you to start thinking about, maybe in the next 20 minutes, and then we start the next part by starting with that. So we are going to have 4 possible states. We are going to have up, down. We are going to have the states down, up. We are going to have states up, down. And we're going to have the states down, up. This is a singlet, this is a singlet, this is up, down, and this is up. The Hamiltonian is going to be the tunneling. I mean, I'm going to go the next. I'm going to have the tunneling Hamiltonian between lattice site C sigma I, daga sigma I plus 1 plus complex conjugated. This is minus J. And then you are going to have the interaction energy that is going to be N up I and damp I. And with that, I'm going to ask you to derive in the large U limit when there are 2 particles in 2 sides, that the dynamics of the spins, or the Hamiltonian that rules the spins, it's set by a Hamiltonian that's in the form sigma dot sigma. Yes? So this is what he derived. Okay. So maybe you can have it's like, well, yes, I think this is short. So I'm going to give you 5 minutes, and then we 5 minutes just to think about it, and I mean it's not and then we derive it and start from there. And if you want, I mean, doesn't add anything else, but if you want to include the states up, up, and down, down, you can as well. No, no, you don't need them, but you can for complexity. Maybe I can give you some hints. It's always better to start with the basis that is the good basis, yes? If you start with up, down, you can do it, but you will have to do calculations. If you use the correct basis, then you don't have to do even a single calculation. So should I start or more time? Yes, thumbs up. Should I start? Okay. Okay. So the idea is that you just start writing the states. What are the possible states? You have up, up, down, down, triplet, and singlet, as usual. This is in the one of the sides. This is on the other side. Can a state up, up, tunnel to the other side? So if I have, can I tunnel? No. So this cannot tunnel, this cannot tunnel. Can this tunnel? No, because tunneling conserves symmetry. So this is triplet, this is triplet, this is triplet. Anything that is triplet, you cannot have two triplet states in the same site. If you have two atoms in the same site, they cannot be in a triplet because of Pauli exclusion principle. The only way that you have in the same site needs to be a singlet because it has to be antisymmetric. So this cannot tunnel. So the only state that can do that can tunneling is the singlet. So the singlet can tunnel to this state, or the singlet can tunnel to these states. These are the two possible allowed, and actually they're going to be equal superposition because it's equal to the right and to the left. So this is the state that it can connect. So the triplet can connect to this state, and the others is 0. So basically, there is going to be a 2 by 2 matrix where the triplet has no energy, this no energy, this no energy, and then you are going to have the state that is antisymmetric has no energy as well because, or has energy U, so there is up, up, down, down, the triplet, and then the state that has, with this minus sign, that the only thing that has is U, because it has the interaction with the minus sign, but it cannot couple, so it decoupled, and the only action happens in the triplet sector. Yes, in the triplet sector, you are going to have this state that can tunnel, and then there is going to be, because the matrix element between these two states, there is an square root of 2. You are going to have a straight through of the tunnel, a straight through of the tunneling, and then you have the interaction U, because this state has interaction U. Yes? So that's the full Hamiltonian. So it's basically a 2 by 2 matrix that you can diagonalize very easily. Now, I put J, or minus 2J. Now, if you are going to look at what happens if U is very large, we are going to do second order perturbation theory. And if second order perturbation theory, then I'm going to have a Hamiltonian where the states that are the triplet, the singlet state here, this state, is going to have an interaction energy that is going to be T squared or J squared divided by U, because you are going to tunnel in the second order perturbation theory. The effective Hamiltonian is always going to be the initial state, the perturbation, that is the tunneling. So let's put the initial state, the intermediate state, the Hamiltonian, and the final state. And the interesting part, the intermediate state has energy U. So this is the process. Yes? So then you are going to have, this is going to be T, this is going to be T, and that's because the interaction and the Hamiltonian has the form T squared over U. Now, let's look at what happens. I'm going to have a Hamiltonian where the triplets cannot tunnel, cannot do that, but only the singlets. So what I need to have to write is a projector into the singlet state. What is a projector into the singlet state? If I have a term that is S dot S minus 1/4, yes? In this case, if I have a triplet, this term is 1/4, give me 0. Any triplet state, because it's SU2 symmetric, give me 1/4, and this term is 0. So this is the projector. When I add S dot S on the triplet, this gives me minus 3/4. Minus 3/4 minus 1/4, 1. So, and that's going to be the Hamiltonian that I need. So, here, square root of 2, square root of 2, and there are two processes. This is here, this is the 2, sorry. So this is what gives me 4, and I'm calling it J. Sorry, sometimes I call it J, sometimes I call it T. So this gives me the 4J squared over U S dot S. This is the Hamiltonian. So that's what we derive. And you can see this is positive. And this is what it emphasizes, that the singlet state is the one that is going to tunnel. So the question that I have is that what happens if instead of having fermions, I give you a boson? So I'm going to give you a boson in two internal states, two different internal states that can have the same process. What would that be different in that case? Nothing? Yes, there is a very important detail that is quantum statistics. So if you have bosons, let's go back, or let's do that here for bosons. If I have a boson that is up, can I tunnel? Can this tunnel? Can this tunnel? All of this and this? Cannot, because two identical bosons, two bosons in the same ground band, when you have a symmetric state, you need to have a fully symmetric state. So the only way that you can, this is antisymmetric, so it's ruled out for bosons. So for bosons, the Hamiltonian, therefore, has to be a projector into the triplet state. So for bosons, assuming, it can be that U up, U down, and U up, down are different. But if they're the same, then you're going to have a Hamiltonian that is 4j squared over U again. But then the point is that you're going to have, in this case, you're going to have S dot S. What is the projector into the triplet state? Is SOS plus 3/4. And when you have the singlet state is going to have, when you have the singlet state, this is going to be this minus 3/4 plus 3/4 is 0. When you have the triplet state is 1/4 plus 3/4. And the sign here becomes minus, because what means is that the triplets are the ones that are going to have lower energy. Yes, the triplets are the ones that are going to tunnel, and therefore they're going to have lower energy. In this case, the singlet is the one that is going to tunnel and is going to have the lower energy. So everything is the same in principle, but the quantum statistic matters a lot. So yes, and that's why when you are talking about, for example, the Hobart model, at half filling, when you have one particle per site, you want to form singlets as the preferable state. This is the Hamiltonian that you have. All right, so yeah. So what we are going to do, then I'm going to stop here. So this is the process. And what I'm going to tell you is how the story is going to change. Now we have a spin-orbit coupling. Because in spin-orbit coupling, the states in one lattice side are going to be different than the other lattice side because the phase is different. So what we're going to try to explore is what is the consequence of SU spin-orbit coupling in the dynamics of fermions in optical lattice and the consequences. We are going to see how we can create cluster states, cat states, and if I have time, I'm going to tell you also a little bit about the Kondo lattice model. All right, more questions? Okay, so we continue. I know 3 hours is a lot, and hopefully I'm not boring you. And if at some point you're saying, please stop, we need some 5 minutes to relax, let me know. Okay, see you after coffee.